By now, I'm sure you know that in just about anything you do in life, you need numbers. In particular, though, some fields don't just need a few numbers, they need lots of them. How do you keep track of all those numbers? Well, mathematicians dating back as early as ancient China came up with a way to represent arrays of many numbers at once. Nowadays, we call such an array a matrix, and many of them hanging out together, matrices. Matrices are everywhere. They are all around us, even now in this very room. Sorry, let's get back on track. Matrices really are everywhere, though. They're used in business, economics, cryptography, physics, electronics, and computer graphics. One reason matrices are so cool is that we can pack so much information into them and then turn a huge series of different problems into one single problem. So, to use matrices, we need to learn how they work. It turns out you can treat matrices just like regular numbers. You can add them, subtract them, even multiply them. You can't divide them, but that's a rabbit hole of its own. Adding matrices is pretty simple. All you have to do is add the corresponding entries in the order they come. So the first entries get added together, the second entries, the third, all the way down. Of course, your matrices have to be the same size, but that's pretty intuitive anyway. You can also multiply the whole matrix by a number called a scalar. Just multiply every entry by that number. But wait, there's more. You can actually multiply one matrix by another matrix. It's not like adding them, though, where you do it entry by entry. It's more unique, and pretty cool once you get the hang of it. Here's how it works. Let's say you have two matrices. Let's make both of them 2 by 2, meaning 2 rows by 2 columns. Write the first matrix to the left, and the second matrix goes next to it and translate it up a bit, kind of like we're making a table. The product we get when we multiply the matrices together will go right between them. We'll also draw some grid lines to help us along. Now, look at the first row of the first matrix and the first column of the second matrix. See how there's 2 numbers in each? Multiply the first number in the row by the first number in the column. 1 times 2 is 2. Now do the next ones. 3 times 3 is 9. Now add them up. 2 plus 9 is 11. Let's put that number in the top left position so that it matches up with the rows and columns we used to get it. See how that works? You can do the same thing to get the other entries. -4 plus 0 is -4. 4 plus -3 is 1. -8 plus 0 is -8. So, here's your answer. Not all that bad, is it? There's one catch, though. Just like with addition, your matrices have to be the right size. Look at these two matrices. 2 times 8 is 16. 3 times 4 is 12. 3 times... Wait a minute. There are no more rows in the second matrix. We ran out of room. So, these matrices can't be multiplied. The number of columns in the first matrix has to be the same as the number of rows in the second matrix. As long as you're careful to match up your dimensions right, though, it's pretty easy. Understanding matrix multiplication is just the beginning, by the way. There's so much you can do with them. For example, Let's say you want to encrypt a secret message. Let's say it's math rules. Though why anybody would want to keep this a secret is beyond me. Letting numbers stand for letters, you can put the numbers in a matrix and then an encryption key in another. Multiply them together and you've got a new encoded matrix. The only way to decode the new matrix and read the message is to have the key, that second matrix. There's even a branch of mathematics that uses matrices constantly called linear algebra. If you ever get a chance to study linear algebra, do it. It's pretty awesome. But just remember, once you know how to use matrices, you can do pretty much anything.
Every matrix paints some kind of picture, while matrix manipulation or arithmetic tells a story. And that's not just the one of how boring this can be in school. At least for me, the beginning of matrices was one of my least favorite parts of math. So I wanted this to at least show you what this all looks like with cool 3D software, as well as an application I never learned in school. So here we go. When you're given a matrix, it can often be useful to think of it as a set of vectors. I'll be working mostly with 3x3 matrices, and you can think of these both as a set of 3 column vectors or 3 row vectors. We'll look into each. Where the column vectors come in immediately is when we use this matrix to represent a system of equations. Here I'm sure most of you know this gives you 3 linear equations. For example, the first is 1x plus 2y plus 4z equals some b1, and the rest of the matrix is all the other coefficients. But another way to visualize this same thing is to write it as a sum or linear combination of the column vectors, where x, y, and z are now just scale factors. Here the first equation would be 1 times x plus 2 times y plus 4z equals b1, the exact same thing. So given some system to solve, you can visually think of this 2 ways. For the first option, you say, if I were to graph each of these, or in this case 3 planes, where do they all intersect? Because that intersection is our solution x, y, z, and in this case it'd be 1, 1, 1. Now I'm going to switch to GeoGebra real quick because it's better for vectors. But the second option says to instead take the columns of our matrix and consider them as vectors. Then find which scale factors are needed such that those vectors add tip to tail to get some other vector b1, b2, b3. So instead of an intersection, we're looking for scale factors. And in this case, all of them would be 1. Just add the vectors together as they are, thus 1, 1, 1 is our solution, just like we saw before. So we have 2 totally different visualizations for the exact same question. I like using the intersection one when I have to solve for x, y, and z, but when I'm asked what are the possible outputs here for b, then I like thinking of vectors. Now I'm going to change the matrix just a bit and also make the b vector all zeros. This then changes the other equations, and now let's go back to the 3D plot. Here we have the first and third equation, and unless they're parallel, 2 different planes will always intersect in a line. Now if the remaining plane happens to intersect that same line as well, which it does, then we have an entire set of solutions x, y, and z such that all these equations are 0. The name we give to those solutions is the null space. It's just the intersection of all your equations when they equal 0. Often that solution is just 0, 0, 0, but sometimes there's more. Here the null space is one-dimensional, just a line, in 3D space. Now on your homework you wouldn't graph 3 planes, most likely. You'd do something like Gaussian elimination, where you take 2 equations, multiply one or both by a constant, and cancel out one of the variables. But instead of just multiplying by -2 immediately, I'm going to sweep the constant from 0 to -2, and watch what happens to the resultant function, which currently is just that second graph in pink. So look, you can see when you add any 2 of these linear equations, regardless of the scale factor in front, their intersection, or the null space in this case, is preserved. The new plane just rotates about that intersection. So we may have a totally different plane here, but we haven't lost the solutions, so we can just replace either equation 1 or 2 and still go through with the analysis. but now the arithmetic is a little easier because one of the coefficients is 0. If you do the same thing with equations 1 and 3, then one plane actually becomes another. This happens because if we replace equation 3, these last two planes are the exact same now. That means if we were to continue the elimination, we get a row of all zeros. And for square matrices at least, a single row of zeros means we have a single free variable. This tells us we have infinitely many solutions to the system, and we say z can be anything, it's free. But x and y depend on that value, so we don't just have any solution. Those dependent variables correspond to something called pivots. And since there's only one free variable, then our null space will be one-dimensional. And by the way, if we did have three planes that only intersect at a single point, then the elimination eventually leads to a plane of one variable, like in this case z equals 1, and from there we would backsolve to get y and x. But anyways, now I want to complete the picture by putting back the original equations and graph. Now what if I told you that the dot product of the vector 1, 2, 4 and some random vector xyz is 0? Well, that means these two vectors are perpendicular. But look, the actual dot product, or 1x plus 2y plus 4z equals 0, is our first equation. And xyz represents the null space, that line of solutions. So our equation says the first row vector of our matrix, 1, 2, 4, is perpendicular to the null space. And the second equation says the second row vector is also perpendicular to that same line, and same with the third. These are all just dot products being equal to 0. And the set of all vectors perpendicular to the null space line is this plane here. And this is what we call the row space. This is always perpendicular to the null space. It contains the three row vectors, all three are in that plane, and it also contains every linear combination of those row vectors. So we have a one-dimensional null space and a two-dimensional row space, which add to 3, and that matches this dimension of the matrix. Just note that this will always be true. But don't forget, these equations, which represent planes, and now we know also dot products with the null space, can also be thought of as a combination of the column vectors. Since this is the exact same question, we already know there are xyz solutions to this that sum to the 0 vector. It's just all the values that made up that null space line from before. So there are infinitely many scale factors that make this work. And when a set of vectors can combine to the 0 vector, given scale factors that aren't all 0, then those vectors are linearly dependent. Or you can also say one of these vectors is just a linear combination of the other two. Same thing. When you have a square matrix with linearly dependent vectors, it means those vectors don't span the entire space they're in. They're confined to like a line, or in this case, a plane. All the column vectors are found here, and also all of their linear combinations, all possible tip-to-tail summations. The name we give to that plane that the vectors span is the column space. See, often you could put any 3 vector here and find a solution, which would mean the vectors are linearly independent. But in the dependent case, we can't have any solution. The output vector has to lie within this plane, the column space, in order for a solution to exist. The column space and the row space, which I'll throw in here as well, usually look very different, but they're always the same dimension. Both are 2D in this case. For non-square matrices, the row and column space are way different. Here the column space is just the xy plane. These 4 vectors can only combine to some other x, y vector. But the row space is the plane spanned by these 2 vectors in 4-dimensional space. However, both those spaces are planes that are themselves 2-dimensional, so that aspect does match. But graphically, these are very different. Now, with regards to elimination, the obvious reason as to why this is important is because it's used to solve systems of equations. When there are many of those equations, which can come up in circuits or other physical systems, then we might not solve things by hand, but we do have to tell computers how to get a solution. However, there's even more of a picture and story beyond just solving these equations, and that has to do with graph theory and networks. Let's say we have some directed graph with 4 nodes and 5 connecting edges, and I'll actually label all these edges E1 through 5 and the nodes N1 through 4. Now, you can think of this like a circuit, where the edges are either resistors or a battery or whatever where current flows, and the nodes would all have some specific voltage. In fact, I'll change the labels to voltages to stay consistent with this. Then the arrows would sort of represent current, although we can't know the direction yet until, at least here, we know if the voltage is positive or negative. Now, we can represent this network with something called an incidence matrix that will have 4 columns for the 4 nodes and 5 rows for the 5 edges. To fill this in, just consider the first edge. On the graph, it's coming out of V1 and going into V2. So we put a -1 under V1 and a +1 under V2. The rest are zeros since they aren't connected to E1. E2 is then coming out of V2 and going into V3. So we put a -1 under V2 and a 1 under V3, then zeros for the non-connected nodes. This is all there is to it. -1s for the out of nodes and +1 for the into nodes. So the rest of the matrix would look like this. Now when we multiply this matrix by a vector of the voltages, it equals every difference between connected nodes, or really potential differences. That's like the voltage drop across a resistor or a battery. So now, what does the null space of this matrix represent? Well, remember, the null space is all the solutions here, or the voltages, that output all zeros or no potential differences. Which is like asking which voltages will result in no current. Well, I'm not going to show it, but using Gaussian elimination we get this matrix here, which again has the same null space. All we did was rotate the higher dimensional equations around their intersection. And this matrix has 3 pivots and 1 free variable. This means V4 can be whatever, and the rest of the voltages are dependent on what we pick. I'll say V4 equals some arbitrary t, and since the other equations are just going to lead to V4 equals V3, V3 equals V2, and V2 equals V1, then every variable would have to be t, or whatever V4 was selected. This is our null space, just a line in 4 dimensions. We can pick something for V4, like ground or 5 volts or whatever, and so long as everything is the same, then we have no potential differences or really no current. Yeah, it's pretty obvious if you know your circuits, but it gives you an idea of what the null space really means here. And with regards to the row space, if you were asked whether some vector is a part of it, or can it be made by combinations of the rows, then all you gotta do is see if it's perpendicular to the null space. And doing a dot product, we see that it is, since we get out 0. In fact, so long as all these numbers add to 0, then it's definitely in the row space for this matrix. One thing that did have some more meaning though is the elimination we did. To reiterate, what we have here is the original incidence matrix on top and the reduced matrix on bottom. The original graph looked like this, but now I'm going to plot the graph or network associated with the bottom or reduced incidence matrix, which would give us this here. It's the same graph minus 2 edges, but the thing to realize is that it has no loops, meaning it's a tree, and it turns out this will always be the case. Every connected graph reduces to a tree. And certain rows or edges that create loops, like this one that represents this edge, eventually reduce to all zeros. So we can say cycles lead to dependent rows since they reduce to 0. Also, the dimension of the row space, or 3 in this case, means you can have 3 edges in this graph without any loops, but any 4th edge will create one. Lastly, the column space is just what all the columns can combine to, or any possible output vector be, from a linear combination of these vectors. If you go through with the analysis, you find the columns combine to any vector so long as b1 plus b4 minus b5 equals 0, and b1 plus b2 plus b3 plus b4 equals 0. This definitely has a physical meaning. I'm using the letter B as a filler, but really B1 is just the first row summation, so really V2 minus V1. B4 is V1 minus V4, and B5 is V2 minus V4. So these values really just represent potential differences between two connected nodes. And bringing back our original graph in circuit form, we find those are the voltage drops in this loop. Thus the potential differences in this loop sum to zero. And this is a fundamental law of circuits known as Kirchhoff's voltage law. It emerges from analyzing the column space of the matrix. And by the way, the other equation corresponds to the larger loop where the voltages must also sum to zero. So if you were given a vector and had to determine whether it's in the column space, you just need to see whether it obeys Kirchhoff's voltage law. This vector does not, because this loop fails to sum to zero, for example, thus it's not in the column space. Everything we've seen here might not be what you typically learn when it comes to elimination, row and column spaces, and so on, but within linear algebra there's almost always an interesting picture or story going on beyond what your textbook is telling you. And if you want to dive deeper into what we've seen here, as well as more advanced topics, you can check out Brilliant.org, the sponsor of this video. To continue with the applications of matrices and linear algebra, Brilliant actually has several courses to learn from. First, their linear algebra course covers all the basics of matrices, but it even gets to adjacency matrices, the use of matrices in graph theory, and unique applications like the Google PageRank algorithm. You can go beyond this though in their differential equation series, which covers underdamped systems, matrix exponentials, and even more advanced applications like laser technology and the associated equations. Covering this wide range of applications really does help connect all the little pieces of linear algebra, from determinants to eigenvectors to diagonalization and so on, so you gain a much better understanding of the big picture. And as you can see, Brilliant courses all come with intuitive animations and tons of practice problems, so you know you have a solid understanding of whatever topic in math, science, or engineering you're interested in learning.
The fundamental, root-of-it-all building block for linear algebra is the vector. So it's worth making sure that we're all on the same page about what exactly a vector is. You see, broadly speaking, there are three distinct but related ideas about vectors, which I'll call the physics student perspective, the computer science student perspective, and the mathematician's perspective. The physics student perspective is that vectors are arrows pointing in space. What defines a given vector is its length and the direction it's pointing. But as long as those two facts are the same, you can move it all around and it's still the same vector. Vectors that live in the flat plane are two-dimensional, and those sitting in broader space that you and I live in are three-dimensional. The computer science perspective is that vectors are ordered lists of numbers. For example, let's say you were doing some analytics about house prices, and the only features you cared about were square footage and price. You might model each house with a pair of numbers, the first indicating square footage and the second indicating price. Notice the order matters here. In the lingo, you'd be modeling houses as two-dimensional vectors, where in this context, vector is pretty much just a fancy word for list, and what makes it two-dimensional is the fact that the length of that list is 2. The mathematician, on the other hand, seeks to generalize both these views, basically saying that a vector can be anything where there's a sensible notion of adding two vectors and multiplying a vector by a number, operations that I'll talk about later on in this video. The details of this view are rather abstract, and I actually think it's healthy to ignore it until the last video of this series, favoring a more concrete setting in the interim. But the reason I bring it up here is that it hints at the fact that the ideas of vector addition and multiplication by numbers will play an important role throughout linear algebra. But before I talk about those operations, let's just settle in on a specific thought to have in mind when I say the word vector. Given the geometric focus that I'm shooting for here, whenever I introduce a new topic involving vectors, I want you to first think about an arrow, and specifically, think about that arrow inside a coordinate system, like the xy plane, with its tail sitting at the origin. This is a little bit different from the physics student perspective, where vectors can freely sit anywhere they want in space. In linear algebra, it's almost always the case that your vector will be rooted at the origin. Then, once you understand a new concept in the context of arrows in space, we'll translate it over to the list of numbers point of view, which we can do by considering the coordinates of the vector. Now, while I'm sure that many of you are already familiar with this coordinate system, it's worth walking through explicitly, since this is where all of the important back and forth happens between the two perspectives of linear algebra. Focusing our attention on two dimensions for the moment, you have a horizontal line, called the x-axis, and a vertical line, called the y-axis. The place where they intersect is called the origin, which you should think of as the center of space and the root of all vectors. After choosing an arbitrary length to represent 1, you make tick marks on each axis to represent this distance. When I want to convey the idea of 2D space as a whole, which you'll see comes up a lot in these videos, I'll extend these tick marks to make grid lines, but right now they'll actually get a little bit in the way. The coordinates of a vector is a pair of numbers that basically gives instructions for how to get from the tail of that vector at the origin to its tip. The first number tells you how far to walk along the x-axis, positive numbers indicating rightward motion, negative numbers indicating leftward motion, and the second number tells you how far to walk parallel to the y-axis after that, positive numbers indicating upward motion, and negative numbers indicating downward motion. To distinguish vectors from points, the convention is to write this pair of numbers vertically, with square brackets around them. Every pair of numbers gives you one and only one vector, and every vector is associated with one and only one pair of numbers. What about in 3 dimensions? Well, you add a third axis, called the z-axis, which is perpendicular to both the x and y axes, and in this case, each vector is associated with an ordered triplet of numbers. The first tells you how far to move along the x-axis, the second tells you how far to move parallel to the y-axis, and the third one tells you how far to then move parallel to this new z-axis. Every triplet of numbers gives you one unique vector in space, and every vector in space gives you exactly one triplet of numbers. Alright, so back to vector addition and multiplication by numbers. After all, every topic in linear algebra is going to center around these two operations. Luckily, each one's pretty straightforward to define. Let's say we have 2 vectors, one pointing up and a little to the right, and the other one pointing right and down a bit. To add these 2 vectors, move the second one so that its tail sits at the tip of the first one. Then, if you draw a new vector from the tail of the first one to where the tip of the second one now sits, that new vector is their sum. This definition of addition, by the way, is pretty much the only time in linear algebra where we let vectors stray away from the origin. Now, why is this a reasonable thing to do? Why this definition of addition and not some other one? Well, the way I like to think about it is that each vector represents a certain movement, a step with a certain distance and direction in space. If you take a step along the first vector, then take a step in the direction and distance described by the second vector, the overall effect is just the same as if you moved along the sum of those 2 vectors to start with. You could think about this as an extension of how we think about adding numbers on a number line. One way that we teach kids to think about this, say with 2 plus 5, is to think of moving 2 steps to the right, followed by another 5 steps to the right. The overall effect is the same as if you just took 7 steps to the right. In fact, let's see how vector addition looks numerically. The first vector here has coordinates 1, 2. And the second one has coordinates 3, -1. When you take the vector sum using this tip-to-tail method, you can think of a 4-step path from the origin to the tip of the second vector. Walk 1 to the right, then 2 up, then 3 to the right, then 1 down. Reorganizing these steps so that you first do all of the rightward motion, then do all the vertical motion, you can read it as saying, first move 1 plus 3 to the right, then move 2 minus 1 up. So the new vector has coordinates 1 plus 3 and 2 plus -1. In general, vector addition in this list of numbers conception looks like matching up their terms and adding each one together. The other fundamental vector operation is multiplication by a number. Now this is best understood just by looking at a few examples. If you take the number 2 and multiply it by a given vector, it means you stretch out that vector so that it's 2 times as long as when you started. If you multiply that vector by, say, 1/3, it means you squish it down so that it's 1/3 the original length. When you multiply it by a negative number, like -1.8, then the vector first gets flipped around, then stretched out by that factor of 1.8. This process of stretching or squishing or sometimes reversing the direction of a vector is called scaling. And whenever you catch a number, like 2 or 1/3 or -1.8, acting like this, scaling some vector, you call it a scalar. In fact, throughout linear algebra, one of the main things that numbers do is scale vectors, so it's common to use the word scalar pretty much interchangeably with the word number. Numerically, stretching out a vector by a factor of, say, 2 corresponds with multiplying each of its components by that factor, 2. So in the conception of vectors as lists of numbers, multiplying a given vector by a scalar means multiplying each one of those components by that scalar. You'll see in the following videos what I mean when I say that linear algebra topics tend to revolve around these two fundamental operations, vector addition and scalar multiplication. And I'll talk more in the last video about how and why the mathematician thinks only about these operations, independent and abstracted away from however you choose to represent vectors. In truth, it doesn't matter whether you think about vectors as fundamentally being arrows in space, like I'm suggesting you do, that happen to have a nice numerical representation, or fundamentally as lists of numbers that happen to have a nice geometric interpretation. The usefulness of linear algebra has less to do with either one of these views than it does with the ability to translate back and forth between them. It gives the data analyst a nice way to conceptualize many lists of numbers in a visual way, which can seriously clarify patterns in data and give a global view of what certain operations do. And on the flip side, it gives people like physicists and computer graphics programmers a language to describe space and the manipulation of space using numbers that can be crunched and run through a computer. When I do mathy animations, for example, I start by thinking about what's actually going on in space and then get the computer to represent things numerically, thereby figuring out where to place the pixels on the screen. And doing that usually relies on a lot of linear algebra understanding. So there are your vector basics, and in the next video, I'll start getting into some pretty neat concepts surrounding vectors, like span, bases, and linear dependence. See you then!
Have you ever heard of an economy being taxed